just call it out.
Here's the story of Mr. Wade's evolution. I taught mathematics at this institution, but then came March. They postponed school. COVID-19 was playing us like a fool. I snuck back in and taught some AP, but they locked up the building and cut the AC. I got frustrated and wrote some sick rhymes. I filmed a rap video just to pass time. I started teaching lessons from my house in Brentwood. Oh wait, you're not supposed to see my real house. I started teaching lessons from my house far away, but I missed writing on a board every day. I talked to my friend Steve Smith, computer hacker. We had to find a whiteboard and he's no slacker. We looked around the city, we finally scored, and now I'm back teaching from a dry erase board. Now we're off Schoology, every single grade, and that's the story of the evolution of Wade.
It's time for a brand new chapter in AB, lesson 4-1 in the Mr. Wade curriculum, and we've got a graph. All right, so we've got two questions. On what intervals is this graph concave up, and on which intervals is this graph concave down? So, concave up and concave down. We loosely talked about it back in integrated classes. Now we're going to officially talk about it in calculus. X squared, y equals x squared, is concave up. But y equals negative x squared is concave down. It's not about is the roller coaster going down or is it going up. Like here the roller coaster is going down, here it's going up. No, it's more about is the curvature of all the cars in the roller coaster, are they all facing up or are they all facing down? Okay, so concave up is kind of facing up, concave down is facing down, a little bit different than increase decrease. All right, can everybody see that this curve is concave up right in here until you get to the 2? At 2, the roller coaster changes. So instead of going down and curving around like this, I have to bend my arm the other way now, right, to go around that. So this region is considered concave up. This region is considered concave down. There's a vertical asymptote, so this is a crazy graph right here. And then it goes back to being concave up. See how that's concave up? You don't need the full U shape to be concave up. You can be like an exponential decay and still be facing up. See how it's facing up? It's not facing down, right? Like this. Okay? So, here we go. Where is it concave up? From the beginning of time, negative infinity on the x-axis, all the way up to 2 on the x-axis. Negative infinity to 2. All right, remember this in integrated 3? Parentheses, nobody can get to negative infinity. Parentheses means can't get there, not including, excluding. At 2, is it concave up at 2? No. Is it concave down at 2? No. It's concave neutral. It's concave 0. Neutral concavity. So, parentheses, not concave up at 2. That's the changeover. Then it's all concave down, and then after 10. So from 10 on the x-axis to infinity on the x-axis. 10 to infinity, but not at 10. There's not even a graph at 10. It doesn't even exist at 10. Parentheses, and nobody can get to infinity. And we put a union in between. So those are the spans, the domain, the area where it is concave up. Now, where is it concave down? From 2 to 10. But not at 2 and not at 10, so you use parentheses. So those are the concave down intervals, or the single concave down interval. So hopefully now you have this mental picture as to what does concave up look like, what does concave down look like. Now for the calculus connection, because we would have never made this connection back in integrated classes. When a curve is concave up, there must be some way to measure that in real life. Like what if you had an equation but you didn't know what the picture looks like? How would you figure out where it's curved upward or curved downward and all the applications in engineering and architecture that use that? Well, it turns out that concavity, the act of being concave, is measured by not the first derivative, but the second derivative. How about that? Real life math for you right here, engineering. And so it turns out when a curve is concave up, its double derivative is positive. So let's make a little arrow right here, and we're going to say f double prime plus. All right? That makes sense, right? Positive is up, negative is down, of course. When a graph is concave down, its double derivative of its equation is negative. There you go. Real life application of the double derivative, fascinating. And then where is it neither concave up nor concave down? Well, at 2, it was concave neutral. So how do we find those places? Because that'll be very important. Matter of fact, today I'm going to give you an example of the stock market and how Mr. Wade saved his family $100,000 because of the double derivative and this little point right here. You don't think calculus is important? Did you hear the number I just told you, $100,000? Do you understand the words that are coming out of my mouth? All right, so 2 is concave neutral. How would you find the concave neutral place? Would you be surprised if I told you that's where f double prime is equal to 0? Concave neutral, makes sense, right? Now, what if the graph doesn't even exist? Then we talked about this before. Remember continuity, differentiability, twice differentiable? That's coming back now. If the graph doesn't exist, then by a domino effect, the first derivative also doesn't exist because the first derivative describes slope. There's nothing there to describe the slope of. The second derivative describes concavity. If there's nothing there, then the second derivative at the vertical asymptote would be does not exist, right? Like, how would you describe the second derivative and the concave up or down if there's no graph there? And then the third derivative doesn't exist, and then the fourth derivative doesn't exist, and then all the derivatives don't exist at x equals 10, okay? Because of the original function. So, notice that the separation between concave up and concave down is either concavity equal to 0 or concavity does not exist. See how that changed from concave down to concave up around it does not exist? So apparently we need to be figuring out where the double derivative is 0 and where the double derivative does not exist, because those are the boundaries that we used over here, 2 and 10, between the two worlds. Wait a minute. Is anybody having flashbacks here? I hope somebody is. Isn't this the same as the last test? Case 1, set the derivative equal to 0. Case 2, set the derivative equal to does not exist, basically. But it's just with the double derivative instead of the first derivative. So it's going to be just like the old test, except it's now concavity, and it's now the second derivative, and then you draw a number line. Very similar. Case 1, case 2, my friends. So now let's see if the double derivative actually works. Oh, it does. It tells you real life concavity. So, letter A, keyword concave. We'll get to the down part later, but concave, concavity. We're going to do f double prime, or y double prime in this case. The down part, we'll get to that later. That's going to be a negative sign. So we're just going to do a double derivative because it says concave. Easy. Now, if it's an easy graph from back in the integrated classes, like if I gave you y equals x squared, you'd say, oh, concave up. If I gave you y equals x cubed, snake, you'd say, oh, well, it's concave down over here and it's concave up over here. You're not supposed to know what this graph looks like. You're supposed to know your basic graphs for this class, but you're not supposed to know what a more complex graph like that looks like. It doesn't even serve you any purpose to know what that looks like. Trust the math. It will tell you where a graph that you can't even visualize is concave up and concave down. So, first, we better rewrite this 1 over x minus 2. That's not derivative ready. Isn't 1 over x minus 2 the same thing as x minus 2 to the negative first? And now we take two derivatives. Y prime equals derivative of x squared, 2x. Derivative of x, plus 1. Derivative of x minus 2 to the negative first, negative 1 to the front. Base stays the same. Drop the power by 1 to the negative second. Chain rule of the original base is just a times 1. So don't have to worry about the chain rule this time. Still think it. That's just the first derivative. Today we are going into second derivative territory. Derivative of 2x is 2. Derivative of 1 is 0. The negative 2 comes down times negative 1 becomes plus 2. Base stays the same, x minus 2. Drops to the negative third times the chain rule of x minus 2, which is again 1. Don't worry about it. Don't anybody out there make this silly mistake, because even good calculus students make this silly mistake. Don't do 2 plus 2 is 4. Okay? It's not. I mean, it is, but it's not. PEMDAS. 2 times the parentheses. It's committed to the parentheses. Addition comes later. Multiplication is what it's connected to. All right? So you can't add those two 2's. So I'm going to write 2 plus. Now over here, this is a house, that's a house. In this house, x minus 2 goes downstairs. Under the 2, not the other 2. That's a different house across the street. The x minus 2 cubed now, positive 3. Looks like that. That is your official double derivative right there. Okay? And how do I know where it's concave down? Well, find the boundaries. The zeros, the does not exists, right? Either one of those. Those are your boundaries for your final answer. Okay? So we need to find the markers, the critical numbers, the landmines, right? So remember case 1? See, I was referring to case 1 right there. Okay, case 1. Take your double derivative now, set it equal to 0. Okay? So let's set this equal to 0. All right, now, remember that stuff we've been talking about on the videos and the things we've been saying in class? If your x group is positive, why would you alter that? If it were negative, you'd move it over. It's positive, leave it alone. Subtract the 2 from both sides. So you get 2 over x minus 2 quantity cubed equals 0 minus 2 is negative 2. Okay. Now, problem. X is on the bottom. We want x on the top, not the bottom. So let's make this negative 2 over 1. Remember the cross multiplication? We did almost this exact same problem in the last chapter. So 1 comes up, times 2 is 2. Parentheses comes up and just sits next to negative 2. Doesn't really do anything there. And now you've got the x off the bottom. It worked. Now divide both sides by negative 2. So if you divide by negative 2, you'll get negative 1 over there. Over here you get cancellation, and you get x minus 2 quantity cubed. Thank you, Mr. Wade. You should be thanking me, because I gave you a perfect cube. If you have a quantity cube, I'm going to give you a negative 1, or a positive 1, or an 8, or a negative 8, or a 27, or a negative 27. Remember all your perfect cubes, just your basic ones? Take the cube root of both sides. The cube root of negative 1 is negative 1, just like the cube root of negative 8 is negative 2. And over here, you've now taken the cube root, which cancels the cube. So remember how to do that from the old integrated classes. Then add 2 over to the other side, and you get x equals 1. That is going to go on my number line. And don't forget, there's also a case 2, though. Case 2. Is there any place that the double derivative does not exist? This is very reminiscent of chapter 3, isn't it? So you should feel very comfortable with this. If your derivative has an x in the denominator, that's the only time you need to think about the does not exist case. Hey now, we can't have a 0 in the denominator. That would imply plugging in 2 for x would be bad. So this double derivative does not exist at x equals 2, because you'll get a 0 in the denominator. X equals 2. That one's easy. You just look at it and get it quickly. The case 1 takes a little bit longer sometimes. Okay, that's it. 1, 2. Oh, we did have a case 3 back in chapter 3. Case 3 was only for piecewise functions in the phase change. This is not a piecewise function. I don't see a curly bracket over here, right? So let's go over here. We're doing a double derivative test today, very similar to a first derivative test, only slightly different because it measures concavity instead of increase, decrease. So on the double derivative test, let's put down the results of case 1 and 2. We got a 1 and we got a 2. Ironically, we actually got a 1 for case 1 and a 2 for case 2. That never happens. Lucky. All right. Now, pick sample points, test points. Don't step on the landmines. Don't pick 1 or 2. Pick any other number in the world. So like 0, great number. Do not make a mark, remember, on 0, because that'll confuse you. Only make marks for your case 1 and 2 results. Number between 1 and 2, you're probably all tempted to pick 1.5. You try to steer away from decimals in calculus, okay, and in college. 1.5. I mean, you almost don't use mixed numbers after elementary school. Sometimes I wonder why they teach them. I don't know. I mean, they have a little bit of importance, but not much. Improper fractions. You should be using improper fractions from integrated 3, even integrated 2, all the way through the rest of your life. So in between 1 and 2, let's not call it 1.5. That'll only confuse you over here. I would call it 3 over 2. Okay? That would be the best way to write that. All right? Be a good calculus student. Bigger than 2, how about 100? Okay, plug them into the double derivative because it's a double derivative test. We're testing the double derivative. We're testing the waters at 0 and 3 over 2 and 100. Is the water too hot? Is it too cold? Okay, take 0, put it in for x. 2 plus 2 over 0 minus 2 is negative 2. Negative 2 cubed is negative 8. And plus minus makes a subtraction. That's 2 minus 2/8 or 1/4. That's as far as you need to go. Don't tell me what 2 minus 1/4 is. Just tell me that 2 minus 1/4 is positive. That's all we had to know. Oh, what's happening before we got to 1? Concave up. We got a plus. Okay? So you don't have to sketch these, but you've got this basin right here. It could be a half basin, could be a full basin, but it's a basin. That was kind of like a half basin, that was a full basin. Who knows? Who cares? It's concave up. Now, take 3 over 2. Plug that into the derivative. All right, let's put it over here. 2 plus 2 over 3 over 2 minus 2 is actually 3 over 2 minus 4 over 2, common denominator. 3 over 2 minus 4 over 2 is negative 1/2 cubed, okay? Now, you remember in those old integrated classes how to cube a fraction, cube the top, cube the bottom? 2 over negative 1 cubed is negative 1. Well, we just did the reverse of that a second ago. We just did cube root of negative 1 goes to negative 1 because negative 1 cubed goes to negative 1. 2 cubed is 8. Negative 1/8. Now, keep change flip. 2 divided by negative 1/8 is 2 times negative 8 over 1. Or just negative 8, right? Negative 8 over 1 is negative 8. 2 minus 16. That's all I had to see. Negative. All right? Now finally, let's plug in 100. So we got 2 plus 2 over 100 minus 2 is 98. 98 cubed is gigantic, but 2 over gigantic is practically nothing. That's like saying 2 plus almost 0, okay? That's a really major conceptual thing that we're going to talk about in the second semester, by the way, 2 over gigantic. So you get 2 plus nothing is positive. Or for that matter, 2 plus anything is positive. So you can just walk away at that point. Okay, final answer. Where is this graph concave down? Where it's negative on the double derivative. Parentheses, 1 to 2 parentheses, you're done. It's just that easy, my friends. Now, letter B. You got y equals this long polynomial. Where are the points of inflection? What the heck is a point of inflection? Aha, haven't talked about that yet. Let's go back over to here. Remember this little point right here where the roller coaster was no longer bending this way, it was suddenly bending that way, right? Your arm has to change. So, that is called a point of inflection. A point where you are concave neutral, and the graph is no longer concave up nor concave down, but right in between. The asymptote, where the graph does not exist, is nothing. That's not a point of inflection, even though it is a concavity change. Okay? A point of inflection is a place where the concavity changes. That is a point, a coordinate, not some invisible force field called a vertical asymptote. No. So we're looking for a coordinate. And you know what? There is the word point in there. Yeah, so points of inflection, coordinates. All right, if you see the word inflection, that is the other word besides concave, concavity, that tells you to take the double derivative. Okay? So, y prime equals 6 comes down, 6 over 3, negative 2. X to the drops to the 5th. Plus 5 times 7 is 35 over 2. Think of that as 5 over 1, right? There's no cross cancel with the 5 and the 2. X to the 4th. Minus 4 comes down, 40x to the 3rd. And the derivative of a constant, 7 over 2, is 0. All right, that's the first derivative. I would hate to work with that because that's a messy first derivative. Wait until you see the second derivative. It's nice. I worked it out for you. I did this on purpose. 5 times negative 2, negative 10, x to the 4th. Plus 4 comes down. Don't do 4 times 35, even though you could. That's impractical. When the 4 comes down, 4 over 2 cross cancels and becomes 2 times 35 is 70. Always use your cross cancellation. I've been preaching that for years, right? Can I say preaching in a public school? I've been teaching that for years. Okay. 3 times 40 equals 120. X squared. There's your second derivative. Where are the real life inflection points of a complex graph you can't even picture in your head because it's so crazy? The real life inflection points where the concavity or the bend changes would be located where the double derivative is equal to 0. And also some other things we'll talk about later. But for now, where the double derivative equals 0 definitely has a chance of being a point of inflection. Now, remember integrated 3 and integrated 2. Factoring 101. When you solve something equal to 0, step 1, if there's a GCF, take it out. If there's not one, go on to step 2. I see a GCF. All 3 of these coefficients have a 10. And if the leadoff, called the leading coefficient, if the leadoff number has a negative, you better pull out that negative. You're going to have a harder time otherwise, okay? So bring out the negative as well if there's one in front. 10, x to the 4th, x to the 3rd, x squared. They all have an x squared. Now watch this open some doors for us if you factor out your GCF. Negative 10x squared distributed or times x squared would get me back to negative 10x to the 4th. Negative 10x squared times minus 7x is plus 70x cubed. Negative 10x squared times plus, let me make some space, 12, positive 12, wouldn't that make negative 120x squared? That would work, right? But we undistributed, we factored out the GCF. After you take out the GCF, it's our old favorite game, multiply, add. What makes x squared in front? X times x. 2 numbers that multiply to be 12 and add to be negative 7. Minus 3 times minus 4, or minus 4 times minus 3. Order does not matter. Okay? All that old stuff's coming back again. All right. Take each group and set it equal to 0, and you will have some solutions here. Set that one equal to 0, that one equal to 0, and that one equal to 0. All right? There's only one number squared times negative 10 that could give you 0. Only 0 squared times negative 10 could give you 0. Okay? Divide both sides by negative 10. You'll find out. It's x squared equals 0. All right. Only one number, minus 3, could give you 0. Positive 3. And positive 4. Okay. What was the question? Points of inflection. Points of inflection occur when the double derivative equals 0, or do they? I mean, that's a start. Here's a great mistake that you could make. So you don't want to make this great mistake, okay? It wouldn't be so great for your test grade. But here's this colossal mistake that calculus students can make right here. Well, I set the double derivative equal to 0. I got 3 answers. Therefore, the graph that I can't really picture in my head because it's too complicated of an equation must have 3 inflection points because I got 3 solutions, so I'm going to put down an answer of 3. All right, 3. I guess I'll put that on my test. Wait, Mr. Wade, that's got to be wrong, but why? Remember the number line on Chapter 3's test but now we're going to call it y double prime, right? Don't you have to do a derivative test? Now hold on a second. One of these could be an imposter. All three of them might be imposters. All I know is that the double derivative equals 0. So what has to happen? The double derivative does have to equal 0 here, but also the concavity has to change from up to down or down to up. And it has to be a coordinate, not an asymptote. So the concavity has to change to be an inflection point, you see. It can't just be derivative or double derivative equals 0. So let's plot these. 0, 3, 4. Okay? Now let's plug in some sample points. So a number lower than 0, negative 100. Between 0 and 3, 1 or 2 would be the easiest. You can use a decimal if you really want to, but I wouldn't. Between 3 and 4, it's okay if you put 3.5. I mean, it's better to put 7 over 2, but 3.5, that's actually okay for here. And then bigger than 4, how about 100? So now, when you plug these numbers in, I want you to notice something. We're putting them into the last form of the double derivative that we had. You always plug it into your last form that you set equal to 0, okay, the factored version. Now, you see this negative 10x squared? When you plug anything into x squared, everything squared is positive in math, right? Except for 0 squared is neutral, but see, we already have 0 marked, so we're not going to accidentally pick 0 as a test point. Everything squared is positive times the negative 10 is always negative. Negative 10x squared can only be negative. So don't go through and worry about negative 10x squared for all these test points. No, it's always negative. So the first one's going to be negative, and the other two parentheses are to be determined. Okay, let's go here. Negative, unknown, unknown. Negative, parentheses, parentheses. Negative, parentheses, parentheses. Okay, so get that negative 10x squared out of the way. It's never going to change. It's never going to be anything but negative. Now, x minus 3, negative 100, minus 3, negative. All right? Negative 100, minus 4, negative. 3 negatives makes a negative. All right, 1 minus 3, negative. That's a very sloppy, like a sideways check mark. 1 minus 4, negative. Oh, 3 negatives make a negative. Whoa, wait a second, folks. 0 was an imposter. You were going to count that as an inflection point? It's concave down, still concave down. That happens sometimes in calculus. Sometimes you get numbers that are important in real life, but they don't affect the concavity. But when you do the number line test, you can realize that they're imposters and that they're not part of the answer. Now, what about 3.5 minus 3, positive? 3.5 minus 4, negative. Negative times a negative is a positive. Did the concavity change around 3? Yeah, concave down to concave up. That one's a real inflection point. That's an imposter. See how the concavity didn't change? And 100 minus 3 is positive, and 100 minus 4 is positive. Plus, plus, minus times a plus times a plus is a minus. Oh, concave up to concave down. 4 is also an inflection point. So we discovered that x equals 0 was a fake. 3 and 4 were the real inflection points. Now, since you're calculus students taking a college level class, I probably need to mention this to you. If the numbers do not exist in the original function, then they're nothing. And that could happen. That will happen in this chapter. Let's go back over here. Remember the asymptote? If the original function does not exist, then it's nothing. It's not an inflection point. Okay? It has to exist in the original function. Now let's go back over here. Do 3 and 4 exist back in the original function? Are they valid points, or is there nothing there on the graph? Polynomials exist everywhere. Okay? Polynomials are continuous from negative infinity to positive infinity. So yes, 3 and 4 plugged back in for x would give you nice, normal, ordinary numbers. You wouldn't get D and E. Okay? So just make sure for later in the chapter. All right? So, did the double derivative equal 0? Yes. Did the sign actually change? Did the concavity actually change in the original function? Yes. Not for 0, but yes for 3 and 4. And finally, do they actually exist in the original function? Yes. they do. Okay? That's how you do it. Now behold, letter C, we've got draw a graph so that f prime is greater than 0 and f double prime is greater than 0. I've taught this problem for now 30 years of my life. I've never had a single student miss it on the test. Okay? I once had a student so bad at calculus that they missed every test question in the entire first semester except this one. So don't break the streak. Everybody can get this problem right, okay? All you have to do is say f prime greater than 0. What does f prime measure again? Oh yeah, increase, decrease, slope. If the increase, decrease is greater than 0, i.e. positive, wouldn't that mean increase and not decrease, right? So when you see f prime positive number greater than 0, you say original function f increasing. Now we just learned something new today. The double derivative greater than 0, greater than 0 means positive, right? Double derivative, positive number. Oh wait, double derivative positive. Original function f, concave up, right? So it's a combination of the last test and this chapter. So positive first derivative, increase. Positive second derivative, concave up. Draw me any curve that is increasing and concave up. That's it. Increasing, concave up. We've done a graph in integrated 3 that was always increasing and concave up. Exponential growth. There are other examples, but that would be a good one for you to draw. Draw me a nice exponential growth curve. Is that always increasing, getting higher and higher and higher? Yes, it never decreases. Is that always upward curvature, concave up? It is, right? It could be fully enclosed basin or a half basin. That counts, okay? A lot of students, for whatever reason, it's like a security blanket. They like to nestle it into a quadrant. So a lot of students like to, put a little, like a half piece of a hyperbola. They like to put that in the corner. That's fine. It's totally fine. You can put it down here. You can put it over there. Doesn't matter. Now don't do this. Don't get sloppy on the test and have a little down up. Okay, I've had students do that on a sample test. Thank goodness they didn't do it on a test. If you put a little down up in there, I'm sorry, but you got a little decrease. Be careful. Make sure that you're steadily rising. Okay, easy question. Very easy question. All right, now let's go to D over here. Now don't worry, we're pretty much done with this lesson. Letters D and E, there's no math, there's no calculus problem involved. It's a real life application just for fun of how important this stuff is. And we're talking like everything we learn in this class is important. But this in particular, what is A on this graph and what is B on this graph? You notice how erratic this graph is? This graph is like all over the place. I wonder what real life thing this graph is modeling. Is there a real life thing that's erratic and almost unpredictable? Well, yeah, there are a lot of things, but guess what? The stock market is one of them. People try to predict the stock market. People try to get rich off of predicting the stock market. Very few actually can do it, and nobody can fully predict what's going to happen in the stock market. It's too unpredictable. So, A is blank. What's point A? Do you see it right in here? Do you see this basin is concave up, and then this little hill right here is now concave down? So we've got an up to a down. Isn't A an inflection point, right? Inflection point, we just learned about those, a point where the concavity changes from up to down or down to up. Okay, that happened on August 1st. What year? We're about to talk about that. Now, what is letter B? All right, letter B is where we're going up and then it's about to start coming back down. Well, you get more of the picture on the next problem here, but it is going to start coming back down. Is that an absolute maximum? No, it's not the absolute highest. That's up here. It is a relative maximum is what it is. Relative maximum. Remember that one? Any old peak. Doesn't have to be the highest, right? Just any peak. That happened on September 16th. What year? We're about to talk about it. So this is actually, I just took a picture, I took a screenshot of the actual stock market when this happened, and I put it right here for you. All right, so this is a real thing. Now, let's go to letter E and discuss kind of a broader view of what happened. Stock market crashes. Boy, does this matter to adults. Now, to little kids, they don't care about the stock market. But when adults have all of their retirement, all the money they're going to retire with someday, all wrapped up in the stock market because that's just where our 401k ends up. That's where your Roth IRA ends up. That's where all those investments end up. When you're an adult, you're going to care about the stock market because all your money's in there, okay? So, worst stock market crashes. Okay, first of all, honorable mention. Third worst ever, late October of 1929. Does everybody know what happened in late October of 1929? I'm sure you've all heard of the Great Depression. And this is what started it right here. This is one of the major contributing factors. People lost their life savings in the stock market. What was the drop? The drop was actually a 23% drop in the stock market, which is horrible. Okay, that's a lot of money lost. All right, but it gets worse. The Great Depression was the second worst stock market crash until this year, 2020. And I'm recording this. If you're watching this in the future, I am recording this in 2020. All right, so this is very much a current topic. The coronavirus pandemic. March of 2020 began what would become a 25% drop and beat the Great Depression as the second worst drop in stock market history. All right, we're very fortunate though that as of this current taping right now, the whole thing has come back. It's actually come back almost to where it was before. So thank goodness we've recovered that, or we would have lost 25% roughly of our life savings. Not good. And then there is the absolute worst. Number one, worst stock market crash ever. It was about 54%. And that was from September the 16th of 2008 all the way up to March the 6th of 2009. Have you heard of all the issues with the subprime mortgage loans and all that scandal and how they were not loaning money correctly and all that stuff with Fannie Mae? You've probably heard about all this, all right? In 2008 and 9, if you were alive, you were just kids running around the yard, and meanwhile your parents' entire life savings was going down the toilet, and you were just running around, screaming in the front yard. You didn't care, all right? Which is good. That's good that you didn't know what was happening. But the rest of us were losing a lot of money. Now, that is the year I've graphed for you. That's the one we did over here in D, and this is the one we're doing in E. This is a wider view in E. When I said August 1st was an inflection point, that was right before the crash, the worst stock market crash of September 16th, okay? So September 16th, oh, see that's the peak? See the relative maximum? Hey, we were doing pretty good. The stock market was great here. It was almost as great here, and then all of a sudden, plummets. Makes a little recovery. We're like, maybe we're out of it. Nope, down we go again. Maybe we're coming out of it. A little rise. Nope, there it goes again. It's like a roller coaster. Certainly I'm not going to keep plunging downward. The roller coaster's got to change. Oh, good. Oh, no. Down again. Oh, good. Oh, no. Down again. And it bottomed out at C, which is a relative minimum. And we thought on January the 20th of 2009 it was over. But then on March the 6th, down here you see D. Can you see that point? That's kind of low on the board. Yes, you can. All right. That was the absolute minimum in this span of years right here. And finally the stock market started working its way back up, and it's so erratic it's hard to predict. But that was the worst right there, even when we thought it couldn't get worse after January the 20th, okay? So Americans lost all this money right here from where it was down to here, okay? Oh, that loan scandal, you can look it up and read all about it if you forgot it, but you probably remember because it was in your lifetime if you were alive. So, what happened? September 16th, we thought everything was normal when the stock market opened that morning. We had no clue. Nobody in America knew. There were very few people that had warning signs about it. Plunge, all your money goes away. We should have taken all of our money out of the stock market on September the 15th and put it under our mattress at home, and you would have lost nothing instead of losing all that money. Now, how did Mr. Wade save his family $100,000? Well, I'm no master at reading the stock market, but I did notice something. At A is an inflection point. August the 1st was just a normal day. But not only is it an inflection point, where the concavity is no longer concave up and starts to become concave down, but it's also, think about the first derivative. Isn't the first derivative slope or steepness? Isn't the first derivative the slope of the tangent line? Imagine a tangent line right there that rides along the stock market graph. The tangent line goes all over the place, okay? So if you have an inflection point in the stock market, that is completely normal. The stock market will rise and fall. That's what it does, okay? Here's another inflection point. Here's another inflection point right over there. But if you have an inflection point where the concavity changes and plus the additional factor that the tangent line is getting too steep, that's when you could have a crash. It's still not a guarantee, but you could have a crash, okay? So you see this right here. When there is a concavity change plus a very steep tangent line, there's probably about to be a peak and then a plunge. So on a hunch, I didn't know if I was right, but on a hunch, we moved money into a very safe account. And guess what? I was right. There are also times where I could have been wrong, but I got lucky this time. Saved my family $100,000. Using what? Using the first derivative for slope and the second derivative for inflection point. Using basic calculus that all of you can now do yourself, okay? If you don't think calculus is important in real life, check out that problem right there, right? Okay? And then just to wrap this up for the day, the 2020 crash, right? I also predicted that something would happen there as well, okay? I also knew that the coronavirus was coming, so I thought it's a possibility. Then I looked at the inflection point and the slope, and I'm like, oh, this is too much like 2008, all right, where all our money was just going away. So again, my wife and I put it in a very safe place, okay? And guess what? We saved, I won't tell you how much money we saved, but we saved a lot more than $100,000 because we're a lot better off now than we were back in 2008 because my wife and I have been carefully saving money our entire lives. So let's just say I saved my family a lot of money because we've collected it and protected it over the years, okay? Real life calculus, it's important, all right? That's it for the introduction for chapter 4. Now you can watch 4-2 at your own leisure and try the homework.
Hold it now.
Double prime negative. Oh, sorry, I messed it up. Dang it! You're not supposed to know what this graph looks like, okay? That's not even, ugh! So now let's see if the golly. Oh. And we're looking for points of inflection. What the heck is a point of inflection? Wow.